Hello and welcome. I am Dr. G from Master Scholars. This lesson forms part of the Electromagnetic induction series for A-levels. The main focus of today's lesson is going to be on magnetic flux and induced EMF. On the bottom left of your screen, you will find the specification references for the main UK exam boards. Let's get straight into it. First, let us see how we are going to define magnetic flux and magnetic flux density. We use the letter phi to define magnetic flux, and magnetic flux is measured in Webers. The symbol is WB. Magnetic flux is the total number of lines of flux passing through a given area at 90 degrees. B is the magnetic flux density, or the number of flux lines passing through a unit area, and is measured in Tesla. On the diagram, we see an example of a surface represented by the blue circle, which has an area A, and through this area A, we have a certain magnetic flux density represented by the letter B. Then the total flux total magnetic flux will be equal to B times A, where B is measured in Teslas and A is measured in meters squared. In other words, phi is equal to B times A. However, this is for field lines that are at 90 degrees to the surface. But what if our field lines were not at 90 degrees to the surface? In some instances, the magnetic field lines are not always going to be at 90 degrees to the surface. In the diagram, you can see an example where the magnetic lines of flux are at an angle theta to the vertical to the surface. We need to break down the component of B into its vertical and horizontal components, where in this instance B sine theta is the horizontal component and B cos theta is the vertical component. We define the term linking as being at 90 degrees to the surface. In this diagram, we can see that B sine theta is horizontal to the surface and therefore not linking the surface, whereas B cos theta is at 90 degrees to the surface and therefore linking the surface. So the total magnetic flux that links this surface will be B cos theta times A, simply written as phi equals B A cos theta. Let's now consider the case where the lines of flux are going through multiple surfaces. An example of that could be that the lines of flux are going through a coil with N turns. The magnetic flux density is B and the area of each coil is A. Since the magnetic lines of flux link with each turn of the coil, then we define the total flux linkage as being N times phi, and therefore N times B times A. And obviously, if the lines of flux were at a certain angle, theta, then the total flux linkage would be equal to NBA cos of theta. Let's apply what we've learned so far in an example. Consider a coil of area A, which is 0.1 square meters, and through which there is a magnetic field the magnetic flux density of this field is 2.5 times 10 to the minus 3 teslas, and the coil has 200 turns. As you will notice from the diagram, the magnetic flux, magnetic field lines are not at 90 degrees to the surface, and they make an angle of 30 degrees to the vertical. Aim of this example is to calculate the flux linkage through the coil. Please pause the video here and attempt this question. So in order to work out the flux linkage for this coil, we will use the equation where total flux linkage is equal to NBA cos theta. In this question, our N is 200 turns, B is 2.5 times 10 to the minus 3 teslas, A is 0.1 square meters, and theta is 30 degrees. If we substitute the values in the equation, we have 200 times 2.5 times 10 to the minus 3 times 0.1 times cos of 30, which returns a value of 0.043 Weber turns. A change in flux linkage is given the symbol delta phi. The change in flux linkage can be due to two factors. For phi is B times A, then delta phi may be due to a change in magnetic flux density multiplied by the area, or number two, the change in flux delta phi may be due to a change in area of the coil, denoted by B delta A. Let's have a look at an example where we can apply this change in flux linkage. Consider a coil of 100 turns where the area of the coil is 0.2 square meters, and initially there is a flux density through the coil of 0.5 Teslas. After a certain time, the flux density through the coil has changed to 0.2 Teslas. The area remains at 0.2 square meters and the number of turns at 100 turns. The change in flux linkage in this case is going to be n phi and delta phi, and in this case the delta phi is caused by the change in magnetic flux, so it's going to be n delta b times A, and replacing the numbers into the equation, we have 100 multiplied by delta b being 0.5 minus 0.2 times the area of 0.2. Putting this into our calculator, the change in flux linkage can be calculated to be 6.0 Webers. One of the places where flux linkage becomes very important is in Faraday's law. Faraday's law is defined as the magnitude of the induced EMF is equal to the rate of change of flux linkage. So if in our example above we had the flux linkage changing during a certain time, then the flux linkage divided by the time taken for that change would have given us the EMF induced in the coil. Let's take a little example of this. Imagine we have a coil of 200 turns and the magnetic flux density through the coil B changes from 2 Teslas to 0 Teslas. The area of the coil is 0.1 square meters. The change happens in a time for the magnetic flux density to change from 2 Teslas to 0 Teslas is 10 seconds. Then the EMF induced in the coil is going to be change in flux divided by change in time. Change in flux is n delta b times A over delta t, and if we replace our numbers in the equation, we can have 200 turns multiplied by 2 minus 0 Teslas times an area of 0.1 square meters. Total time taken delta t is 10 seconds. Putting numbers in our calculator, so we have 400 times 0.1, which is 40 divided by 10. That will give us an EMF of 4 volts. Not forgetting our units in the equation above, the EMF is measured in volts. Flux linkage, change in flux linkage is measured in Webers, and the time is measured in seconds. Let's consider an example where the experiment is to drop a bar magnet through a coil. As follows. Imagine this is our coil linked to a data logger, which is going to measure the EMF produced in the coil, and a bar magnet. Poles here really are irrelevant. The bar magnet is dropped through the coil such that it goes through the coil and out on the other side of the coil. What I'd like you to do is to plot a graph of EMF versus time. EMF will be on the y-axis and time on the x-axis. Pause the video, give it some thought, and resume the video once you have plotted the graph. So let's have a look at what the graph would look like. We'll have, as I said, EMF on the y-axis and time on the x-axis, and we are going to plot this graph. Now, the graph is going to look a slightly odd shape. Let me draw it first, and then we will discuss it. So let's put the points A, B, and C here on the graph. Between points A and B, the magnet is entering the coil, and also the magnet, at all points through the coil, the magnet will be accelerating. So if the magnet accelerates, it means that the rate of change of EMF or the rate of change of flux linkage is not constant. That means that as the magnet goes through the coil faster, the rate of change of flux linkage is going to increase, and hence why the graph between sections A and B and B and C is asymmetrical. So in fact, I will redraw this graph because the graph here is going to be much taller between B and C. Reason being that the rate of change of flux linkage between B and C is much greater because the magnet is traveling faster. In this question from AQA, we have a graph of magnetic flux phi versus time, and the graph shows us how the magnetic flux changes with time. The question asks us to determine how the magnitude of the EMF V induced in the coil varies with time t. In order to attempt this question, we first need to consider the equation for the EMF, which is given by EMF equals N delta phi over delta t. And this tells us that the EMF is the rate of change of flux linkage. Whenever we have a situation like this, it simply means that if we plotted a graph of flux linkage versus time, the EMF would actually be the gradient of the graph. So let's see how the gradient of this graph changes. Well, we start off with a shallow gradient at the beginning of the graph, going up to a steep gradient, and that will actually eliminate 3 of the options immediately, which is this one, decreasing value of the EMF. Same for this one, and here we have a constant value of the EMF, and therefore the only available option for us is option D. So if we look at option D, we see that the EMF is directly proportional to time, as it's a straight line through 0, and we can't really tell from the graph whether it's going to be a linear relationship, but as I said, it's the only graph where we have an increasing EMF corresponding to an increasing gradient of the graph. Another great question by AQA, this time around asking for us to calculate the magnetic flux cut by an aeroplane wing as it travels at a certain speed. So let's have a look at what the question is asking. So we have an aircraft wing of span 60 meters and traveling at a speed of 150 meters per second, constant speed, and it's traveling through the Earth's magnetic field at which is 1.0 times 10 to the minus 5 Teslas, and the question is to calculate the magnetic flux cut by the wing. So diagram here helps to understand what is going on. So imagine this is our aircraft wing of length 60 meters, and it's traveling at a speed of 150 meters per second, and it does so for 10 seconds. So the area covered by the aircraft wing, represented in this diagram, is going to be 60 times 150 times 10 seconds, and that gives us 90,000 square meters. And in order to find the flux cut by the aircraft wing is simply going to be B times A. Our magnetic flux density is 1 times 10 to the 5 minus 5 times the area of 90,000. 0 too many there, and gives us a flux of 9.0 times 10 to the minus 1 Webers, which is D in our question. A slight variation to this question may ask you to calculate the EMF induced across the wingtips of the aeroplane. This time around we have the wingspan is still 60 meters, traveling at a speed of 150 meters per second, and the flux density of the Earth's magnetic field is 1.0 times 10 to the minus 5 Teslas again. This time around we have no time given for the time of travel of the aircraft. Rather, they've asked for the EMF induced to be determined. So we'll start with the same diagram as follows. Our wingspan of 60 meters, but we'll notice that there is no area given in this case. However, if we consider that the aircraft moves at a speed of 150 meters per second, then the area covered per second, or delta A over delta T, is simply 60 times 150, and that gives us an area per second of 9,000 meters squared per second. So that's the area covered per second, or our delta A over delta T. And we also know that the EMF across the wingtips is going to be given by a delta phi over delta t, and in this case, because it's the area changing, it's b delta a over delta t. Now we have already determined the delta a over delta t, so simply our EMF will become the magnetic flux, which is 1.0 times 10 to the minus 5 multiplied by delta A over delta T, which is 9,000 meters squared per second, and I believe that the answer is going to be 0.09 volts, which is A on the screen. Our final example for this video looks at a graph of magnetic flux density versus time for a field linking coil. The graph, the question in the question asks about how the induced EMF varies with time for this problem. So if we look at the equation for the EMF, E is delta phi over delta t, and in this case our area is constant, but we have a changing magnetic flux density. So the EMF will be delta B times A over delta T. And if we look at this part of the equation, delta B over delta T, that's simply the gradient of the B versus T graph. Here we see that the EMF is going to be proportional to the gradient of the B versus T graph. Looking at the B versus T graph on the top of the page, we notice that we have a shallow constant gradient for both the times of between 0 and T1 and T1 and T2. Both have constant gradients, which means that the EMF is expected to be constant between the times 0 and T1 and T1 and T2. Looking at graphs A and B, both of them show increasing and decreasing values of EMF, so therefore these two values, these two graphs can be eliminated straight away. So it's a choice between C and D. Now, if we look at the gradient between 0 and T1, we see that between 0 and T1, the gradient is much shallower than between T1 and T2. So therefore, the EMF between 0 and T1 is going to be smaller than the EMF between T1 and T2, and therefore our answer for this question is C. So this brings us to the end of this lesson on electromagnetic induction, focusing on magnetic flux, linkage and EMF. I hope this has been useful for you, and if you have found it useful, please subscribe below and press on the like button. This allows This concludes this first part on electromagnetic induction. If you liked the video and found it useful, please click like and subscribe below. I hope to see you all very soon. Take care for now.